All right, guys. So, yeah, welcome back. Here we are back. Just want to review a little bit of what we did last time. Right, we calculated the pH at various stages of a weak acid strong base titration, and I just kind of want to go through the different steps that we worked through and the things that we did in those steps. So we're going to finish up chapter 15 here and get a start in on chapter 16. So the initial pH of a weak acid strong base titration, right? So this is before the any of the base has been added, right? We have a solution that's entirely just the weak acid in solution, and so you just treat this as if it were an acid Ka problem. After you start, and so you'd go about it the same way, assumptions and everything to find your pH. After you start adding base, now you're going to have a mixture of the weak acid and its conjugate base. And so this is one of those times where you're going to look to basically find how much of the weak acid is remaining, how much of the conjugate base you've created, and then use Henderson-Hasselbalch to figure out the pH of this particular mixture. And you can do so, so Tracy just asked a question before we got started, you can do so in terms of either moles or, which is what we did here, or you can convert it back to molarity. I mean, right, you should be converting it to molarity first and then to moles. Or excuse me, and then plugging it into the equation as a molarity. But you can use moles because we're assuming it's the same volume for the solution. Then we looked at a specific point, again, before the equivalence point, while we have this mixture of weak acid and conjugate base, and that specific point is, and this is an important aspect of what we're doing, right? Halfway to the equivalence point. At that point, you've added half the moles of strong base to the acid. So you basically converted half of your weak acid to conjugate base. And so at that point, you have a mixture that's 50% weak acid, 50% conjugate base. So when you plug that into the Henderson-Hasselbalch, right, this piece here, right, or excuse me, the piece here, that is the ratio of the conjugate base to the weak acid is going to equal 1, which means log of 1 is 0. And so you wind up with the pH is equal to pKa at halfway to the equivalence point. And so experimentally, if we're doing that, we would find the equivalence point, look at the volume halfway there, and find the pH at that volume, and we know that that would be our pKa. Then when you get to the equivalence point, at that point, you've converted all of the moles of weak acid to its conjugate base. So now you have a solution of weak base, right? Because the conjugate base of a weak acid is a weak base. And so you would find the new concentration of that, which is what we did over here, right? So that's the initial concentration of the weak base, and you do just a weak base calculation. And something I want to make sure is clear. So one of the things that sort of stuck out to me on the quiz that you guys did is that you had a question that was kind of like this, where you had a weak base in solution. And so if you were given a Ka, then you can find, well, you need to use your Kb to do this particular calculation. And your Kb, right, if you remember, is just 10 to the minus 14 divided by the Ka, right? On the quiz last time, a lot of you, so you were given a pKa, and so something to remember here is that you can calculate the Ka from a pKa, or you can convert it directly to pKb, because the pKb is just going to equal Kw minus Ka. And then, so from that, excuse me, pKw minus pKa. Okay. And so from that, you could determine your pKb, and then from your pKb, you could figure out the Kb. And then from there, you determine the hydroxide ion concentration. Once you have the hydroxide ion concentration, you can subtract, or you can find the pK or POH to, and then the POH will allow you to calculate the pH just by subtracting it from 14. Okay, so that was At the equivalence point, it's a mixture of weak base. After the equivalence point, now you're looking at how much excess strong base you have, and in that calculation, you basically say, hey, the strong base that remains is going to overpower any of the weak base that's there, and so the concentration of hydroxide is just going to depend, again, on the this concentration of the strong base that remains, or that you have left over after converting all of the weak acid to its conjugate base. And so those were the different calculations that we did for the weak acid titrated with a strong base. Now, the reverse of that, okay, is if you have a weak base titrated with a strong acid, right? In this situation, right, your initial stage here, your initial solution is a weak base. From here all the way down to the equivalence point, right, all the way down to there, you're still going to use Henderson-Hasselbalch, okay? And so you're going to use that Henderson-Hasselbalch equation. So it's still pH is equal to pKa plus the log of the concentration of the weak base, or A minus, right, over HA. So in that, with that in mind, your weak base, right, the concentration of weak base in here, right, that's the A minus, right, and the HA is what you're converting that weak base to by adding the strong acid. In this case, we're looking at, say, ammonia and HCl. Okay. And then again, at halfway to the equivalence point, right here, right, at that's halfway, right, the pH there is also going to be equal to the pKa. So in this initial step, where you just have a solution of weak base, right, that's where you're going to use Kb. After that, you need to have Ka in hand. So remember, your Ka is just going to be Kw over Kb, okay? And so, and of course, your pKa will equal 14 minus pKb. So after that initial step in this particular type of titration, you're switching back over to the Ka again, and you're utilizing that. So the only times you use a Kb are really when you have a solution that is just the weak base, and then you'll be in good shape. Okay. And finally here, right, at the equivalence point, you have a solution of just weak acid. Right, so if you have just weak acid, you're using your Ka and the icebox, right, and you're doing the calculation based on an icebox. And then afterwards, you're finding from here on out, right, this is how much strong acid you have in excess. Okay, and that's how you're going to determine your pH there. Okay, so it's sort of like the same process as the weak acid strong base titration, but it's in the reverse direction, if you will. Okay. All right. So we're not going to go through a full calculation example of that. You've got that. You should have that in your practice problems. Be able to do that there. When it comes to polyprotic acids, we're not going to do major calculations with this, but there are certain things you do need to know about a polyprotic acid and strong base. And of course, the reverse would be the conjugate base of a polyprotic acid with a strong acid. And so a couple things here. If you have, say, a triprotic acid, you're going to have 3 equivalence points. Okay, so what you're doing is essentially you start here with a weak acid, and it's just that weak acid solution is really just the triprotic acid. Your initial solution is just this H3A. So this could be phosphoric acid, for example. And so you'd find out the pH of that solution, just like we did with a weak acid initial solution. Right? As you add base, you turn that weak acid into its conjugate base. So this stretch here from the initial point to the first equivalence point, right? That's going to be your Henderson-Hasselbalch equation, where you're using the pKa of the first proton, right? So that would be pKa1. Then at the equivalence point here, you can actually do this a couple of different ways. One, you could look at it from the standpoint of the Kb for the first conjugate base, or you can use it as the Ka2 for the second proton. And so when you have the second proton in solution, basically, and that's really the way you want to go at the equivalence point, is you can look at it from the standpoint of, well, now I have an acid, right, that has 2 protons to it, right? Since we only take 1 proton off at a time, right, I can figure out the pH of, say, if this were a triprotic acid like phosphoric acid initially, this might be something like sodium phosphate. And so you can say, oh, I have a solution of sodium phosphate here. What's the pH of that solution? And so that would be the next thing that you do. And so again, once you get into the next region, right, from here up to the next equivalence point, right, that's the Henderson-Hasselbalch equation. And so for that one, you'd be using pKa2 for that Henderson-Hasselbalch equation. And then you get to that equivalence point, and you can now use your Ka3. And really, we should be using the Ka's at each of these steps. It's a better way of doing it. And so you use Ka3 for that point here, the second equivalence point. And then from the second equivalence point to the third equivalence point, you would use the Henderson-Hasselbalch again with pKa3. And then you get back up here. So if this was phosphoric acid was the initial acid, this would be something like phosphate over here. And so to calculate that, you only have phosphate in solution. So you'd use Kb for A3 minus at that point. And if you go past that, again, this is now excess base. So the big difference is each of these, so you have now 3 equivalence points. And each equivalence point, you kind of start fresh with a new acid, right? And then you go through the Henderson-Hasselbalch till you get to the next acid. Then you go through Henderson-Hasselbalch till you get to the next acid. At each equivalence point, you can consider yourself to have a solution of the acid that's been deprotonated once or twice. And then at the third equivalence point, you now have the conjugate base of, or in other words, where the acid has been deprotonated all 3 times. And that's how you would calculate your pH of that type of a solution. So when choosing a buffer, what's nice about a triprotic acid, right, there are 3 pKa's, right? So if we were to look at back in chapter 14, we looked at just briefly triprotic acids, right? We had H3PO4, for example. We had H2PO4 minus, HPO4 2 minus. Those are all 3 acids, right? That has a Ka1, Ka2, Ka3, and pKa's. pKa1, pKa2, and pKa3. And if you were looking to use one of these acids as your starting point for making a buffer, right? And that's something we're going to see a little bit more as we do the buffer calculation in our making a buffer lab, right? You could start with one of these pKa values, right, and know that if I'm trying for a certain pH, this gives me 3 options for finding, the pKa within plus or minus 1 of the desired pH. So that can be really useful when it comes to figuring out what acid you might want to use in a given buffer solution. And so one of the common buffers out there is actually the dihydrogen phosphate and hydrogen phosphate as a buffer solution because the pH of that comes in right around, so the pKa2 I believe is right around 7 if I remember right. It's pretty close, 6.86 I think is what it is. So anyway, that can be a really useful one for mimicking biological systems. And so that's something to sort of keep in mind as you're going through and thinking about, well, how would you make a buffer to mimic a biological system? Well, this is one system that we can utilize to do so, okay? And so that really talks about titrations for us. With one other thing to keep in mind is, remember, every time that we come to an equivalence point, right? Every time we have an equivalence point, we notice that's the steepest point or steepest part of that curve, right? There, right? To get to that equivalence point, and here, right? That's the steepest part of the curve. So in other words, the pH is changing most rapidly at each of these equivalence points. And so in order to have a good indicator, we really want the indicator to change color, right? If we're doing a titration during each of these really steep points, okay? We want that indicator to change color, right? In this region, right? Or here. Or if we're looking at the titration of the third proton, right? Looking at it changing color there. And so what that means is we need to have an understanding of what our indicators are, okay? So what we want to do here is sort of identify what is an indicator first and foremost. Okay, so to do that, just want you to see, so if we think about what an indicator is, so an indicator is something that changes color, okay? Now, in general, we consider our indicators to be weak organic acids. So when we say organic, they're carbon-based. They usually are going to be something that has, like say, a carboxylic acid to them, okay? And a key here is that weak organic acid is going to have a conjugate base, right? It's going to be a different color than the acid. That way you have an endpoint that's really easily recognizable. Okay, and so that recognizable, what just happened? Come on. There we go. So what you basically want here is since it's a weak acid, you can think about the Henderson-Hasselbalch, where the point at which the region in which it changes, right, are going to be when you go from the pH where it's acidic, right, where you just have the acid, to that point where you have a solution of the conjugate base. And so the color change is going to start to happen, essentially based on the relationship between the protonated and deprotonated version of, for some reason, my computer is being a pain. Don't know why. So let's go back to that page. Not sure why it's doing this. There we go. Okay, so what we're looking at here is we've got a mixture. So an indicator, which we consider to be HIN. So HIN is our indicator. And we have it HIN. The IN stands for indicator, and the H notes that it's protonated. And that, in the reaction with water, of course, gives you a deprotonated version of the indicator. And so essentially, the ratio or the relationship between the amount of deprotonated versus protonated indicator is going to be something that's pH dependent. And so when it comes to an indicator, you want an indicator that has a pKa, right? So this pKa here, you want that to fall in that region where it has a pH where the acid that you're titrating is going to change to its conjugate base to be where the equivalence point is. And so that's going to come where you have a mixture of the ratio of the conjugate base, or the IN minus, the deprotonated indicator, over the protonated indicator, that's in a ratio of 10 to, so 10, so in other words, 10 parts IN minus over HN, right, to 0.1, right? So these two values are the same. So you have 10 times as much conjugate base as much as the protonated weak acid, as compared to 10 times the amount of protonated acid versus weak base. So essentially, it's going to change color between when the pKa is, or the pH is equal to the pKa plus or minus 1. So if you look at something we've used in the past, phenolphthalein, okay, so phenolphthalein changes color between, right out here, between about 8 and 10. Okay, so the reason that we use phenolphthalein for a strong acid, strong base titration, if you think about what the titration curve looks like, right? It goes up really fast and then kind of starts to peak. And so here in this region of that titration curve, that's going to be between, where it changes the most, about 7, right? Is where, when you have a strong acid titrated with a strong base, that's the equivalence point. Well, that changes very quickly. The pH changes very quickly in that titration there. So just when you get a little bit past 7 is when the phenolphthalein starts to change color. And so you really want it at just that glimmer of light pink color for that to be, for it to be right at the equivalence point, right? And so if you've picked your indicator well, that's when you will have a good endpoint that comes right at the equivalence point. Now, that being said, there with phenolphthalein, it just barely turns pink right at as the pH goes above 7. There are other indicators out there that you could use, but something that's kind of useful to keep in mind is, and we're going to go back up to, let me stop the share real quick and find this in, go back up to our image here. All right, let's share this again. Okay, so we're going to go back up. Come on. There we go, to this point. So you'll notice that as we look at the titration curve here, right, the equivalence point here for a strong acid, strong base titration is right at 7, and phenolphthalein changes color, right? If you can see that here, right, this is the range where phenolphthalein changes color. When you first start to see that color change, you're still in that really steep portion of that titration. Now, if you tried to use phenolphthalein as an indicator for a weak acid, it's also very good, right? You can see it still is changing color, right, in that really steep region. So you want to stop the titration right when it starts to change color, in either case where the curve here is really, really steep. Now, you wouldn't want this, the litmus paper for a weak acid titration, right? Weak acid, strong base titration, because as you can see, the litmus paper would change from red to blue in the region between where the pH is about 5 and the pH is 8, right? And so that's really within this region where the a weak acid would be a buffer. And so that's bad because you'd get a false early value for the concentration, or excuse me, for what the equivalence point is, because it would turn that color way too early, right? Now, something like a methyl orange, right, it changes color down here more at between 4 and 3. And so what you could use that as an indicator if you were doing a titration of a weak base with a strong acid, because of the nature of when it would start to change color, right? More towards the end of that weak acid, strong base, weak base, strong acid titration, right? And so picking an indicator is one of those things. You want the pH at the equivalence point to be about the same as the pKa. If not, for an acid titrated with a base, you might want that pH to be, or the pKa to be slightly higher than the pH at the equivalence point. And if you're titrating a weak base with a strong acid, you might want the pKa to be a little bit lower than the pH at the equivalence point. Okay. And so that's where we would have our our indicators to allow us to pick out, when they change color, to figure out what's the best in the wrong direction. Try that again. Sorry about that, guys. All right. So with that in mind, here we go. Okay, so with that in mind, you can see there's a lot of different indicators here, and in one case, one that you've actually used before, for those of you who did the equilibrium lab, the Beers Law lab back in Chem 101, you used bromothymol blue. Wait, no, I have that wrong. You were using a dye. Anyway, so bromothymol blue is an interesting one for us. You can actually use this to figure out, it's kind of a fun one to use to figure out the Ka of the solution. But anyway, it's something we can sort of talk about outside of the class also. But you'll notice there are also a couple of indicators up here. There we go. There are a couple of indicators up here. There we go. As you can see, that have 2 equivalence points. So you'll notice that these 2, right, those ones there and those ones there, right, they have 2 equivalence points to them. So you can tell that those are diprotic indicators. Now, another thing that's interesting about this is if you're looking at trying to make something that's a universal indicator, you can do that with a mixture of these various indicators to sort of have a better feel for the color, how color of an indicator solution is going to give you an idea of the pH of a sample, right? So if you have something like a universal indicator, it's just like a mixture of a bunch of indicators, okay? And so with that, that takes us to the end of chapter 15. So hopefully, as I close this PowerPoint, my computer will work a little bit faster. So what I would ask is, for right now, are there any questions about the chapter 15 stuff or the stuff we've done in chapter 15 today before I close this up and move on to 16? Okie dokie. So then we'll close up. So we'll stop our share here. I'm going to close up that PowerPoint slide, so my computer hopefully speeds up a little bit. Okay. One moment. Okay. And we'll bring ourselves into the next chapter, chapter 16. Okay, So here's our, so we've now done, so chapter 12, kinetics, chapter 13, equilibrium, chapter 14, acid-base equilibrium, chapter 15, more acid-base equilibrium, and now we're going to be into chapter 16, which is equilibria of solubility equilibria. Basically, we're looking at the dissolving of a substance. And so it's just another type of equilibrium. So 13, 14, 15, and 16 are all 4 chapters based on equilibrium. So lots of this thrown at you. So this is going to be treated in a similar manner with some slight differences, and we'll go through some examples to really get familiar with all of this stuff. So chapter 16. So solubility equilibria and the solubility products, the first section. So when we look at a solubility equilibrium, okay, what we're looking at here is it's still an equilibrium, right? It's a little bit different, but not much different, okay? It's still an equilibrium, okay? And so we're gonna treat it in the same way. And so if we think about something like, say, calcium carbonate dissolving in water, right? You have calcium carbonate solid, okay? When you put that calcium carbonate solid in water, right, you dissolve it. As it dissolves, we come over here, we know that each of those ions, right, they dissolve, they go into solution, they become, it dissociates, they become solubilized, they become hydrated. But calcium carbonate is not particularly soluble. It's a little teeny tiny bit soluble, but not very, okay? But it's still the stuff that does dissolve, the calcium 2+ ion and the carbonate 2- ion, it still dissociates. It's just that not much of it does. And so this is a chemical reaction. It occurs when you put a solid substance into water, right? And it dissociates, okay? So if you think about this and you add just a teeny tiny amount of the calcium carbonate, it's not very soluble. So you put, you know, a crystal or 2 of that calcium carbonate into water, right? It's all going to dissolve, right? You can think about that, you know, it's related to the solubility of other things like, say, table salt. You put a little bit of table salt into water, it dissolves. But at that point, you just have a little bit of that substance that's in the solution at all. So if you add a little bit more, right, you're going to continue to dissolve more until you reach a point where if you add any more, right, any more solid added, right, will not dissolve. That's a point that we call the saturation point. So that solution would be saturated, okay? What happens after that point, if you add any beyond it, it doesn't dissolve. It just stays at the bottom of the solution, right? And so you're going to have, essentially, beyond the saturation point, you're going to have solid that just stays at the bottom of that solution. Now, there's an equilibrium going such that ions in the solution will come in and stick to the solid, and some of those solid ions will move out and go dissolve. And so there's an equilibrium between the solid state and the aqueous state. Now, at the saturation point, it's not the same. It's not quite the equilibrium between solid and dissolved because there's no solid dissolved. But past that point of saturation, you have an equilibrium between solid and aqueous salt. Okay. And so you can kind of look at it from the standpoint of now equilibrium, where you have what's called a KSP, so, where the KSP, sorry, this got shifted down a little bit. So KSP is the equilibrium expression for the salt dissolving in water, okay? Now remember that this is calcium 2+ aqueous and carbonate CO3 2- aqueous, right? If we go back up to our equation at the top, right? Those are the aqueous things. We don't include the carbonate in this particular equilibrium constant, like we never do. And so really it's just an equilibrium constant for a solid dissolving to make aqueous stuff, okay? Now it's called the solubility product, right? Don't let the SP scare you off, just like you shouldn't let the KB or the KA scare you off. It should just give you more information. That one shows the solubility of a substance, and it's called the solubility product because, well, it's for the solubility of a salt, right, or of a solid, And it's the product of the ion concentrations of the ions into which the solid dissociates, okay? So for something like calcium carbonate, this has a value that's very small, right? 3.3 times 10 to the minus 9. And so that equilibrium constant, right, 10 to the minus 9, barely any of that calcium carbonate is going to dissolve in water in a reasonable amount of that water, okay? And so these tend to be done, by the way, you'll see at 25 degrees Celsius. So we're doing sort of a standard temperature for solubility, 25 degrees Celsius, not 0 degrees, because we're talking about solubility in water much of the time, okay? And so we're looking at, again, it's the product of the concentrations of the dissolved ions in the aqueous solution, okay? That's what our solubility product is. So before we start to get into some examples, there are a couple other parts to this solubility that we need to explore. Definition-wise, when we talk about solubility, there's a couple ways to do it. And the most common way that solubility is expressed, right, so what we call solubility, it's expressed. So if you were to look it up in a table of physical constants, for example, it's generally expressed in grams of a substance, right, per 100 milliliters of water, okay? Now, that's just sort of a convention. It's just how it's done. So if you wanted to look at something like sodium chloride in water, it's a little more than 35 grams, it's right around 35 grams of sodium chloride that's soluble in 100 milliliters of water, okay? And so that's what we call the solubility. Something you'll also see, though, is the molar solubility. And the molar solubility is really just, well, it's based on molarity. Moles of the salt that dissolve per liter, right, of per liter of the aqueous solution is how this should be. It shouldn't be just per 1 liter of water, it's per liter of aqueous solution, okay? And so the difference being, when we do equilibrium, like ice boxes and the like, those ice boxes are going to allow us to really easily figure out the molar solubility. And from the molar solubility, we can calculate the solubility in terms of grams per 100 milliliters. And we can do that, right, from our KSP values, because our KSP value is related to the molarity of the salt that dissolves in the solution, okay? All right, so let's do an example of this. Again, this is a pretty straightforward example. Let me get my pen back. So what we have here, so our example is going to say, well, calculate the molar solubility and then the solubility of calcium carbonate. So that's our example to start this whole thing. And so to think about this, we want to make sure we have our chemical equation, as we always do, right? Good practice to draw out the chemical equation, and then from that we can make the equilibrium constant expression and the icebox. So here we're looking at calcium carbonate, solid, right, dissolving in water. So I'll put the H2O above the arrow. Occasionally that's something you can do. Above or below arrows tell you something about the reagents that are involved in this reaction. This is just saying I'm putting it in water. That's going to dissociate to give calcium 2 plus carbonate, CO3, 2 minus. Okay, and so there's our chemical equation for this reaction. So I'm going to directly just put together an icebox for this. We've got our initial, our change, and then at equilibrium. Make sure this is all in molarity so it's nice and easy for us to see. Okay. Now with the solid, our solid, as we know, isn't part of our equilibrium constant expression, right? Our equilibrium constant expression, KSP, for the solubility product is going to be the concentration of calcium 2 plus times the concentration of carbonate, CO3 2 minus, right? We don't have to take into account the calcium carbonate because it's a solid, so we're just going to make little dashes there so we have something to stop us from writing anything else there. So we go now to look at our initial concentration of calcium 2 plus. So here we can say, well, before any dissolves, our concentration of calcium 2 plus and carbonate are both going to be 0. For every calcium carbonate that dissolves, we're going to get 1 calcium. So if we say X calcium carbonate dissolves, we get 1 calcium and we get 1 carbonate. So plus X and plus X. So at equilibrium, we have X and X for our concentrations that we can calculate. And so in doing this particular calculation, it's pretty straightforward. Make sure I have the, yeah, good. So in this calculation, we just plug these values into the equilibrium constant expression. So KSP is 3.3 times 10 to the minus 9. That's going to equal X squared. And so you can calculate X will be the square root of 3.3 times 10 to the minus 9. Right? And so you can calculate that. That's comes out to 5.4 times 10 to the minus 5. But we also know that that's going to equal our concentration of calcium carbonate, right? So our calcium ion, Ca2 plus, which is going to equal the concentration of the calcium carbonate that's dissolved. Okay, and so we can say that our molar solubility right, which will be the concentration of calcium carbonate, will equal 5 I'm missing something. It should be 5.74. So 5.74 times 10 to the minus 5, and we have our units in here, molar. So there's our molar solubility of calcium carbonate, okay? So I'm going to take that onto the next page. 5.74 times 10 to the minus 7, excuse me, 10 to the minus 5 molar. So calcium carbonate concentration is 5.74 times 10 to the minus 5 molar. And so from that, we can figure out the solubility by saying, well, solubility, right, will be so grams of CO or calcium carbonate per 100 milliliters. Okay, so in other words, I've got to do two things. One thing I have to do is figure out how many moles there are going to be in 100 milliliters, right? And then once I have the moles per 100 milliliters, I can convert that to grams. Okay, and so it's pretty simple. I start out and say, well, in 100 milliliters, which is 0.1000 liters, times 5.74 times 10 to the minus 5 moles of calcium carbonate per liter. Cross out my units. Should be left with 5.74 times 10 to the minus 6 moles of calcium carbonate. Now, calcium carbonate has a molar mass of 100.086 grams per mole. So I can convert my moles into grams by just multiplying by the molar mass. So the 5.74 times 10 to the minus 6 times 100.086 grams of calcium carbonate per mole. So our units there cancel out, moles of calcium carbonate, moles of calcium carbonate. And we're left with 5.74 times 10 to the minus 4 grams of calcium carbonate in 100 milliliters of that solution. So our solubility will be 5.74 times 10 to the minus 4 grams per 100 milliliters. Okay. All right. Any questions so far? We're going to go through some other examples.
Do you mind going?
What's up?
Oh, sorry. Do you mind going back one slide really quick? Sorry.
Sure. Anything in particular?
So the once we find the concentration of our ions, that will be equal to the concentration of the calcium carbonate.
In this example, yes, because as you see, right, that X, right, is equal to the concentration of calcium 2 plus, which is equal to the concentration of CO3 2 minus. And that concentration of the calcium carbonate concentration comes from, right, this calcium carbonate concentration, right? Because for every 1 calcium carbonate that dissolves, you get 1 calcium and 1 carbonate. That make sense?
Okay, okay. Thank you.
There will be an example where it's not quite that simple, but we'll see that in a minute. All right. So you can also, if you know the solubility, you can actually determine KSP. So for our next example, we'll look at lead fluoride. Okay, so this example says lead fluoride is shaken with water at 25 degrees Celsius, and its solubility is found to be 0.064 grams per 100 milliliters. So we can calculate the KSP. So when you say it's shaken with water, the idea is you're shaking it up, you're trying to get as much of that lead fluoride to dissolve. And then you stop shaking it, you let the lead fluoride that's still solid settle to the bottom, you take 100 milliliters off of the top, that's your lead fluoride solution. So how would you figure out that many grams could be found? Well, you evaporate off of the water, right? And you might do that with a full liter for something that's less soluble. And then whatever, after you evaporate off the water, whatever mass of salt is left gives you your solubility of that substance. And so in this case, we know just based on things that we've done in the past that from the icebox, we can sort of determine that initial concentration to some degree. And something I want to do here is I want to put together an icebox for doing this to make sure we can sort of keep track of everything that we're doing here, okay? So with lead fluoride, it's always good to do this, the equilibrium constant expression and the KSP expression for these. So here, we've got lead 2 fluoride, so PbF2, solid, is going to dissolve to give us, when it dissolves, gives us lead 2 plus, it's aqueous, plus, remember it's 2 fluoride. So if you don't remember your solubility stuff from chapter 4 and how salts dissociate, make sure you go back to chapter 4 and think about, the fact that if you have something like a halogen, right, it doesn't give you the homonuclear diatomic, right? This is an ionic compound, so it's going to give you the halides, right? And so just as a reminder, that's where you'd find that stuff, is when you were doing precipitation reactions back in chapter 4. Now this chapter is sort of an extension of that, but it's from a quantitative standpoint, where we actually have now, for things that we would consider insoluble back in chapter 4, we now know that no, they dissolve a little teeny tiny bit. Now we're just quantifying how much they dissolve, right? So we'll have our initial change and at equilibrium. And now you may not have to always put the icebox together for something like this, but I want to illustrate one thing in particular, okay? Now, as we put this together, before I start to fill it in, I want our KSP expression, right? It's going to be the concentration of the lead 2+ times the concentration of fluoride, F-, squared, because we raise it to the power of its stoichiometric coefficient. So before any lead dissolves, we've got a 0, right? And a 0 for fluoride. For every 1 lead fluoride that dissolves, we get a lead 2+, so plus X, but we also get 2 fluorides, right? So it would be plus 2X. And so at equilibrium, we've got X for the lead 2+ concentration, and we've got 2X for the fluoride concentration. And so all we have to do here is plug this into, should I give myself another page? I did, okay. So all we have to do here is plug this into the equation here, except for the fact that we don't know what X is yet. But we can get that because we can tell how much lead and fluoride are dissolved because we're given this value up here. And that right there is how many grams of the lead fluoride dissolve in 100 milliliters. Well, we want to know how many moles of lead dissolve in 1 liter. And so we need to convert from grams per 100 milliliters to its molar solubility. Okay, so we'll plug that in, that value of X in a little bit. But what we need to do first is calculate it. So here, we're going to take our 0.064 grams per 100.0 milliliters. We're going to convert our milliliters into liters. So 1,000 milliliters for every 1 liter. That gets our units, that gets our units into liters in the denominator, which is good for molarity. Then we're going to convert from grams into moles by dividing by the molar mass. So we divide by 245.2 grams per mole. Okay. Okay. So you wind up with, when you do that calculation, you wind up with 0.00261 molar lead fluoride. And that value is our X. Okay? So I'm going to take that and our KSP expression onto the next page. So we've got KSP is equal to the concentration of lead 2+ times the concentration of fluoride squared. And we know that the concentration of lead 2+ is equal to X, which is equal to 0.00261 molar. Okay. But our concentration of fluoride at equilibrium is equal to 2X. So if we multiply that by 2, we wind up getting, right? So 2 times 0.00261 molar, which gives us 0.00522 molar, right? F-. Okay. And so what we can do here is just plug those values in. KSP is equal to, right, 0.00261 times, and I can keep it simplified if I want to, but if you just want to plug it in as 2x, you can say times 2 times 0.00261, which is the same as 0.00261 times 0.00522. And you wind up with a KSP of 7, forgot to square it. I need to square that, and I need to square that. And so you wind up with a KSP value of 7.11 times 10 to the minus 8. Okay, and so you can now calculate KSP from a solubility, or for that matter, from a molar solubility. We because we calculated the molar solubility first, and then we calculated the KSP second. Okay. Any questions before we go on to our next example? Okay. So the last thing I want to do today is sort of, we're going to do one more example in here today of the KSP, basically using KSP to calculate solubility. And I do want to do that for calculating the solubility of something like magnesium hydroxide because of the nature of how we approach these, okay? So if we think about the reaction for magnesium hydroxide, okay? Magnesium hydroxide, MgOH2, solid, right? So if we're going in the reverse of what we just did, it's important to be able to sort of do the math and approach our calculators, right? So when we do this, right, we're dissolving that in water. It gives us magnesium 2 plus 2 hydroxides. Okay, and just based on what we just did, we can put together that icebox in the same way. Okay, so we put our icebox together in the same way. We don't worry about the magnesium hydroxide. Our initial concentration of magnesium 2 plus is 0, and hydroxide is 0. For every magnesium hydroxide that dissociates, we get a magnesium 2 plus, so there's plus X, but we get 2 hydroxides, so plus 2X. So at equilibrium, we have X and 2X. But now we have our equilibrium constant to work with. And so we need our equilibrium constant expression. KSP is equal to the concentration of magnesium 2 plus times the concentration of hydroxide squared, okay? And then we just plug in our values. So 8.9 times 10 to the minus 12 is equal to X times 2X quantity squared, right? Because we're just taking that 2X from there and plugging it into there, right? And so as we work this out, we can see that's going to be X times 4X squared, which is 4X cubed. So now we're dealing with something that has a cube. So that's an issue for us if we've never dealt with a cube before, okay? So we've got that is going to equal, and I'll just bring my 8.9 times 10 to the minus 12 to the other side. Okay, so I can divide each side by 4 to get my X to one side. So I get X cubed equals 8.9 times 10 to the minus 12 divided by 4, which will be where's my value? 2.225 times 10 to the minus 12. okay? And so X will just be the cubed root of 2.225 times 10 to the minus 12. Okay, so that's the cube root though. So in your calculator, depending upon the type of calculator, you need to figure out how to do this. And so that's why I wanted to get to it today, really you need to make sure that, so in a lot of calculators, you would type in the 3, right? And then you would have this X square root value, right? And then you would type in the thing that goes under the square root, or the cube root after that. Right, so 2.225 times 10 to the minus 12, right? So that's our X, right? Where this X down here is just part of the function in your calculator, at least if you have a TI, okay? And so you would wind up doing the math on that. You would get a value of 1.286 times 10 to the minus 4. Ooh, minus 4, okay. Erase that, do that again. Okay. So that's your X value. Okay. So if we know X is equal to 1.286 times 10 to the minus 4, that's also equal to your concentration, in this case, of the magnesium 2+. Right? And the concentration of the fluoride is just twice that, right? But that concentration of magnesium 2+ is the same as the concentration of magnesium, excuse me, not fluoride, hydroxide, OH2. Okay, and so that would be 1.286 times 10 to the minus 4 molar, right, would be the molar solubility of the magnesium hydroxide, okay? If you're calculating the solubility, right, we got to convert that to moles per 100 milliliters, right? Okay, so here, 0.1000 liters times 1.286 times 10 to the minus 4 moles of magnesium hydroxide per liter gives you 1.286 times 10 to the minus 5 moles okay. And so when we take that value, that's moles of magnesium hydroxide, and knowing the molar mass of magnesium hydroxide is 58.319 grams per mole, and we can use that to figure out the solubility based on the number of moles we just calculated. So 1.286 times 10 to the minus 5 moles times 58.319 grams per mole should wind up with 7.46 times 10 to the minus 4 grams of magnesium hydroxide in that 100 milliliters. H2, there we go. And so our solubility is going to be 7.46 times 10 to the minus 4 grams of magnesium hydroxide per 100 milliliters. Okay. And that is where we will end for the day. So are there any questions on that one? I think the hardest part, at least for when you initially do this is sort of this stuff over here, right? Doing the cubed root. So make sure you spend some time with your calculator to explore how to do a cubed root. If you have to go look up a manual to do it, by all means do so. If you want to, talk to me in office hours on how to do it, I'll be happy to help you out with that. Okay. I'm going to stop our recording right there.